Hey everyone, it's me, Miss B, and today's video we are looking at Unit 4, Lesson 6, and these are the cumulative practice problems for illustrative math geometry. So, in this lesson, we basically learned that all of the ratios that we've been working with have formal names, and those are sine, cosine, and tangent. So, we are going to select all true statements relating to that in question 1 here. So we have to be careful about which angle we're using. So they're using a theta and beta. This one here, this symbol, this is theta. And then this symbol here that looks like a B, this is beta. These are just Greek letters. So that's which ones I'm referring to when I say those names. So we want to look for sine of theta, and we know that these follow SOHCAHTOA. So one of the ways you can write SOHCAHTOA, it's SOHCAHTOA, but I also like to write so, ka, and toa, like this, because that tells me opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent for each of these, and the S, C, and T stand for sine, cosine, and tangent. So if we want sine of theta, that means we are here. We are looking at opposite over hypotenuse. Which one is opposite? That's 4. Which one is hypotenuse? 97. So is sine of theta 4 over the square root of 97? You bet it is. So that's going to be our first answer here. A is a true statement. Now we're looking at the tangent of beta. So from our perspective here, 9 is going to be the opposite, and 4 would be our adjacent. So tangent is opposite over adjacent. So we would say beta, we want opposite over adjacent, so 9 over 4. This one is also correct, so that is a true statement. Now it then says below it that the tangent of beta is 4 over 9, which is incorrect because it cannot be both of those, so it just is incorrect. So our next one is cosine of beta. So we're still over here at angle beta, and well, angle B, but the measure of that is beta, number of degrees. So cosine of beta, cosine is adjacent over hypotenuse. So our adjacent from right here is 4, and square root 97 for our hypotenuse, so 4 over 97. That one works. And then they are telling us that 4 squared plus 9 squared should equal 97. This should be right because we would have the two legs be congruent to the hypotenuse squared. But if we wrote this all out, just to give an example, this would then be 16 plus 81 is 97, and 97 is equal to 97, so that checks out. So E is also correct. So the only one that's not true here is C. Now, if they said instead of tangent beta, if they said tangent of theta for that one, that would be correct. It would just be the reciprocal of the tangent of the other one, but they didn't, so that's the only one that's wrong. That brings us to question 2. We're supposed to write an expression, almost said equation, very different things. Write an expression that can be used to find the length of JH, and an expression that can be used to find the length of GJ. So they want to know length of JH. So JH, that's this one here. And then GJ, that's this one here for GJ. Okay. I am going to I know they want an expression, but it's easiest for me to set this up as an equation. So I'm actually going to write it as an equation, but then solve it for the variable that is missing, and then leave it in the expression form and not simplify it to a number. So if we want to find JH in relationship to the only angle they're giving us, this is going to be the opposite side. and GJ is going to be the adjacent side, because 9 is the hypotenuse, and that is across from the 90-degree angle at J. So what can we do? We can use both sine and cosine of 35 to individually find our opposite and then our adjacent, using our hypotenuse. So I know that the sine of 35 should be equal to whatever that opposite side is over my hypotenuse. So it's that opposite side over 9. And so to find that opposite side, or to find JH, I'll actually write JH in here. That would make more sense. So this would be JH over 9, and this was the green one. Then we would multiply both sides by 9 here, so that JH, the expression we could use to find it, would be 9 times the sine of 35 degrees. And I'm not going to actually simplify that one in a calculator, just going to write it out that way because they're asking for an expression that can be used to find the length. So this right here is that expression. There we go. We're going to do the same thing for the adjacent one. So we're going to use cosine of 35. And that is going to be equal to GJ, or our adjacent, divided by the hypotenuse, which is also 9. So I'm going to highlight just for colors so that everything's consistent. That one we're using cosine, so we would multiply here both sides by 9, which would mean that GJ, to find that length, we would do 9 times the cosine of 35. And we are not, again, not going to actually simplify and find a numerical answer. We're just going to solve for the expression because that is what they said here. They said write an expression. So that means we don't necessarily have to solve. Okay, for number 3, we have Andre and Claire, and they're discussing a triangle that has a right angle at C and a hypotenuse of 15. Andre thinks that the triangle could have legs of 9 and 12, and Claire thinks that angle B could be 20 degrees, and then side BC would be 14.1. Do you agree with either of them? And explain or show your reasoning. So let's look at the 3 sides first. So that would be Andre's, the legs that are 9 and 12. So that would mean specifically that Andre's triangle would look a bit like this one. If this was 15, then this would be 9 and 12. And if you can recognize it, this is actually a multiple of 3, 4, 5, which we know is a right triangle, but we can still show that here. We're going to show 9 squared plus 12 squared should give us 15 squared. So this would be 81 and 144, and we want that to equal 225. Just to double check myself, kind of actually off screen, just check this on a calculator because sometimes I make silly mistakes. 81 plus 144, yep, 225. It does work. I didn't want to be like one off and then thinking that this was a multiple when it wasn't. So I do agree with Andre that it could be a right triangle. The only other one that we're talking about is Claire's, and Claire is probably correct as well, because these 2 triangles don't have to be congruent in order to have a same length hypotenuse. So Claire was saying that we would have B 20 degrees. So I'm going to draw hers a little sideways here because I want to make that angle 20 degrees. Close enough there. and we'll make our triangle here. Okay, so if this is our 90 degrees, we could have the hypotenuse is still 15, and she said BC would be 14.1, and that this would be a 20-degree angle if this is angle B. And so A would be here. So we're going to check hers with a trigonometric ratio, or basically using the 20 degrees and sine, cosine, or tangent. Now in this case, we have the hypotenuse, and we have from 20 degrees, and I'll just put myself standing here. I like to draw a little person where the angle is at. This is going to be the adjacent, so I would be looking to do the cosine of 20 degrees and have that be equal to 14.1 over 15. So I can do both of those on my calculator and compare the two numbers. So, because I don't have a variable I'm solving for here, we can type in cosine of 20, and calculator says this is 0.93940 actually. So 940, and then for 14.1 divided by 15, this comes out to exactly 0.9494. And then, so the rest would be zeros. So I agree with both. So I'm going to say both could be correct. We would need to know more information about the triangle to know which one it needs to be. Okay, so that brings us then to question 4. So question 4, we have a triangle with side lengths 5, 12, and 13. We want to draw the triangle and then verify it's a Pythagorean triple, and then approximate the acute angles in this triangle. So I think we did this on our previous assignment. Let's go back and check. It might have been a different one. We did an 8, 15, 17. So we're going to do the same thing here with 5, 12, and 13. So let's draw a triangle here. I'm going to draw myself a right triangle, see if I can't make it decently shaped. Okay, 5, and then we'll go with 12 and 13. Okay, so that means that this smaller side here is going to be my 5. The 12 would have to be this leg, and then 13 would have to be the hypotenuse. The longest side is always going to be the hypotenuse. So we drew the triangle. Now, the next step they're asking us to do is verify it as a Pythagorean triple. So let's use the Pythagorean theorem. We are going to test 5 squared plus 12 squared and verify that that makes 13 squared. 5 squared is 25, 12 squared is 144, and 13 squared is 169. And yes, it turns out when we add them up, 169 is equal to 169. So we have verified it's a Pythagorean triple by just showing the Pythagorean theorem. Now to approximate these angles, we could use what we learned with sine, cosine, and tangent in this one, but we still want to stay in practice with what we've done with our tables, because there is going to be on our test a section where you are expected to use that table of values. So we are going to choose an angle here. So I'm going to choose, I like to use the angle that is on the quote unquote ground, so to speak. So I'm going to call that theta. And generally, like, I draw a little picture and I pretend that's me right there. That's my perspective. So that means that 12 would be the opposite side. 13 has got to be the hypotenuse because it's across from the 90. It's always the largest number. And then that means that 5 is my adjacent side. So I always like to label just in case so I don't make any mistakes. We want to approximate some acute angles. So we're going to do that with theta, and then we're going to subtract from 90 to get what our other angle would be. And I guess we can follow along with their pattern, and we can call our other angle beta when we get there. So this is theta degrees. We want to see how large theta is. So let's do, I like to do opposite over hypotenuse for sine. I know the last time we did one of these, I think I used adjacent. Or you know what? We can even use opposite over adjacent and get some tangent going on here. So let's do, for, we're going to do opposite over adjacent. So we're going to say for theta, opposite over adjacent, and that's going to be, in our case here, the 12 divided by the 5. So 12 over 5. And then I'm going to create a decimal approximation of that by doing that on a calculator. So 12 divided by 5. This gives me 2.4. Exactly. There is no further decimals. It's just 2.4. So we're going to be looking under our third column on our little table. The third column is going to be tangent. So if I zoom out, I can put a large version in here and then make it small so we can actually read it when we zoom in. Okay, so we are looking at opposite over adjacent. Maybe I'll just leave the tiny version of this table in here. We're going to look at opposite over adjacent. So really what we learned today was this is cosine and sine and tangent. Now I am looking for 2.4 to show up here. I see it starts really small and it ends at like 5. So the closest thing I see is 2.7. But it's not going to be in between 2.7 and 5. It's actually going to be in between here because we have 2.4 between 1.732 and 2.747. So that is between 60 and 70 degrees. And since that's about, this is almost a span of 1. It goes from 1.7 to like 2.7. So our number was 2.4 exactly. This is closer to this value here, which means it's going to be closer to 70. So I'm actually going to just highlight these rows on here so that afterwards you can actually see like, hey, these were the rows I thought it was in between. And this would be between 60 degrees and 70 degrees. And we're going to say closer to 70 degrees. So at this point, we can just estimate. I would say that that means that it's not quite going to be like 65. It would be somewhere in between 65 and 70 if I'm saying that it's closer to 70 degrees. But the main idea here is that you're putting it in between those numbers. So I might say this is, oh, we'll go with 67. Yeah, 67 works good for me. So we'll say theta is approximately equal to 67 degrees. And then we can label this one up here beta, which is like that weird curly looking B. So then I can say beta is approximately equal to, I don't like the way I drew that. Beta is approximately equal to, and we're going to say 90 minus 67, which is, I believe, 23. But I just like to check myself anyways. 90 minus 67, 23. That was correct. So 23 degrees. Now, if you were not 1 or 2 decimals, 1 or 2 degrees off from this, that's fine. As long as yours really follows between 60 and 70, but closer to 70, you should be fine. So I will put a little box around this to mark this as my answer. That box is not lining up nicely. Here we go. That is my answer for that one. So that's going to bring us then to the back page, where we have questions 5, 6, and 7. So question 5 is going to be a lot of consulting on our table because it does say approximates. So if you're approximating, you're going to use your ratio table. So I'm actually going to put another little copy of that ratio table, another big copy, but I'm going to make it little. And I'm going to put it over to the side here. So that's not by default printed on yours, but just so that I have a reference page on here for me. So let's actually move it a little bit closer while we are looking at this one. So since we have A, B, C, and D, I am going to try to use some highlights to show different colors here, which ones I'm talking about in the table. I'm going to start with yellow, adjacent over hypotenuse. So A, we're going to go with yellow, adjacent over hypotenuse. That's going to be my first column. Oh, actually, you know what? I can put a little dot in the first column there. And that is 0.966. So I see that it is between these two right here, 0.98 and 0.94. So somewhere between 10 and 20. And 0.966 seems about halfway in between. You can actually subtract. You can do the average of these two if you want to find what the halfway distance is by adding them up and dividing by 2. Or you can just kind of eyeball it. This looks about halfway, so I would say approximately, I'm just going to say approx 15 degrees, because that looks like it's between 10 and 20. Okay, so for B, I will use green, and hopefully I'm not going to highlight some of the same stuff, but this is now opposite over hypotenuse, so I'm going to use opposite over hypotenuse. And for that one, we are looking at 0.469. So if we look here a little further, 0.469, that is going to be in between these two values right here. So in order to use those, we are now looking at in between 20 and 30. So 0.469, that's about 0.47. 0.47, that's going to be pretty close to 5. So, or 0.5, which is for 30 degrees. So I'm going to say it's a little closer to 30 than it is to 20. And I will approximate this one. So we're not going to say 25. Let's just say 27 degrees. As long as you're not saying exactly 20 and exactly 30, and yours is somewhere in between, you should be okay, but still, it's better to try to get as close as you can. Okay, now I'm going to highlight here blue for my adjacent over hypotenuse. That's my second piece that's going to go in the first column, so I'm putting another little highlight there. Adjacent over hypotenuse, 0.309. So if we look closer here, 0.309 is going to land in between these two values down here at the bottom, 0.342 and 0.174. So it looks a little bit closer to the 0.342, so closer to 70 degrees. So between 70 and 80, definitely closer to 70 degrees. So let's put approximately, and we can do, it's not super close, but let's just do like, instead of 75, maybe we'll just do like 70, maybe 74, which is closer to 70 than 80, so we'll say like 74 degrees. And again, it's an approximation, so we just want something that makes sense. Last one, I'm going to highlight pink just so that you all can see what I'm talking about. And this one is opposite over adjacent, so that answer I'm going to put in my last column, or use from my last column. And this one is 1.036. So 1.036. I have some things that are pretty close here at 1.19, but then I have to figure out, is it this way or is it this way? It's increasing as it's going downwards, so I actually do need to use the one above it. So it's going to be in between these two values. And for us, that means going all the way over to the side, it is in between 40 degrees and 50 degrees. I would say this is pretty close to like 1.2, and this is 0.84. If we're using 109, it's going to be pretty close to 1.2 or closer. So we're going to say it's going to be in between the two of those. Oh, I'm sorry, it's 1.036. Yeah. This is going to be closer to 50 degrees. It is going to be closer to the all of this. I can move a little closer actually. So I didn't realize I wasn't going to need to do as much work with it, but we'll say that this is closer to the 50 degrees. So I'll just say, it can even just say that this is 45. So we'll say this is approx, and yeah, it's closer to 50, so I'll just say like 46 degrees, something similar to that. Remember, it's an approximate. There's going to be some wiggle room in it, as long as yours is making sense. And hopefully my color coding makes sense here if you're looking at those. So you can see like what column I'm looking in and then what two numbers I'm looking at to approximate where I'm going. That then brings us to number 6, which is right here. So Lynn missed class, and Tyler is helping her use the table to approximate the angle measures that have the ratios listed. Tyler says you can use the right triangle table to figure this out. And Lynn notices that some of the ratios are repeated in the same, some of the ratios are the same in each row. Estimate the angles and explain why some of the values are repeated. So let's go back to our handy dandy little chart for this one. It's not going to be so little when I first put it in here, but we'll make it littler and maybe stick it right off to the side. So using our chart, 0.573. So we're going to start here. And once we actually, I'm going to use this chart, and I don't actually need a ton of stuff because we do know that our angles should be complementary because these are flip-flopped. So as long as I can make an estimation on both, we can actually make that work. So 0.573, and that was adjacent over hypotenuse. So we're looking in this column for adjacent over hypotenuse. 0.573. Okay. So 0.573 is going to be in between these two right here. In between 0.5 and 0.64. So this is actually right about halfway. So I'm going to say that this is probably like 55 degrees. Which means this one down here should be 90 minus 55, and that would be 35 degrees. Now I can use my table to verify those numbers. I'm not going to highlight everything on my table, but I am going to check, do these pieces work for 55? And then do these ones work for 35? So let's look at that row. We want 0.81 and 1.4. Does 0.81 fall between these two? Yes, it does. And 1.4 definitely falls in between those two, so we're good there. Now we want to look at the 35. So 0.819, 819, 573, and 7. So 819, yep, falls in between those, and we're looking at between 30 and 40, it's 35 degrees. 573 would be in between there. Then what was our last one? 0.7. Yeah, 0.7 is definitely in between all of these. So these all check out, and 35 works. It's always good to verify your stuff here. So explain why some are repeated. I'm going to put as my explanation down here, the the complementary angles have repeated values because the opposite side of one is the adjacent of the other. Yeah, basically when they're complementary, meaning they're in the same triangle or they add up to 90, the complementary angles, the opposite side of one angle is going to be the adjacent side for the other. And that is what causes these to switch because we have opposite and adjacent. So if we're using the adjacent leg here, that's going to be the opposite leg for the other, and the hypotenuse stays the same. I just didn't have a whole bunch of room to write that long paragraph of an explanation, so hopefully I think this shorter one works. Very last question. We want to find the length of each leg and then show our work. And this is from Unit 4, Lesson 3. So if you see down here, we have Unit 4, Lesson 3. So I am actually going to do this using right triangle, special right triangle ratios. Because this is a 30 and a 60 degree angle, we can call that this is a 30, 60, 90. And we know that the short leg should be the equivalent of x, the hypotenuse should be the equivalent of 2x, and the longest leg would be the equivalent of x times the square root of 3. So if we're finding the length of each leg, I just kind of like to do the math right on here. Basically, to find x, we would divide both of these sides by 2, and 4 divided by 2 is 2. This is x, so that means here x is equal to 2. So I can say QP is 2. And then I like to take this number here and just plug it straight in. So this would be 2 times the square root of 3. And so then I can say RQ equals 2 square root 3. And just because you might be asked this on a quiz of some sort, and they might not allow you to use the word root to represent it, let's just look at our decimal approximation. So let me grab out my calculator again that I didn't realize I was going to use another time here. So give me just a moment. Okay, so 2 square root 3. Our decimal approximation of this is 3.464. Or, so I'll say, or approximately. That's the same thing as like the wiggly lines here. 3.464. And there should be enough there if you need to round that you can. So that is our 2 root 3. And these would be my 2 answers to this. So I'm going to put a box around these. And that makes the end of our assignment. So Thank you for watching. Hopefully my explanations helped. And this has been the Unit 4, Lesson 6 Cumulative Practice Problems for Illustrative Math Geometry.